Today I'm going to talk to you about valence electrons, and we're going to go over some concepts called shielding and effective nuclear charge, which are going to help us make predictions about periodic trends tomorrow in class. Now, if you remember back to the last video that you watched, we talked about nitrogen and we did the electron configuration for nitrogen. So nitrogen has 7 electrons, but when we did the abbreviated configuration, we saw that the abbreviated configuration is helium, 2s2, 2p3. Okay, and what that tells us is that electrons in the outermost shell, or the 2 sublevel, are the 2s electrons, there's 2 of those, and the 2p electron, and there's 3 of those. Okay, and those electrons, the ones in the outermost shell, are the valence electrons. And we represent these valence electrons with a symbol called the electron dot symbol. And an electron dot symbol is a convenient way for us to represent the valence electrons as shown by dots on the side. So for example, if we look at nitrogen again, 2 plus 3 is 5. So nitrogen has 5 valence electrons, and the electron dot symbol for nitrogen would look like this. And it doesn't really matter which sides the dots go on, just that there's the right number total, and you put 1 on each of the 4 sides, and then you start doubling up if you get more than 4 electrons. And one neat thing about the way our periodic table is organized is that each group has every member of that group has a set number of valence electrons, and we can determine that by the group number. So for example, hydrogen, lithium, sodium, all of the alkali metals all have 1 valence electron. The alkaline earth metals all have 2. If you go over to the noble gases, they all have 8, except for helium, which is an exception. And then the halogens all have 7, and so on. So this is our periodic table, but you could just imagine the transition elements being stuck in this region here. And these are the group numbers that are at the top of each of the groups on your periodic table. So you can just look at your periodic table and know how many electrons how many valence electrons a particular atom is going to have. So you could go to carbon, for example, and if it's in group 4A, and so you know that means that it has 4 valence electrons. In addition to telling us about the number of valence electrons, there's a lot of information on the periodic table about other properties of elements as well. And those properties tend to vary as you either go across the periodic table or as you go down the periodic table. And so we call them periodic trends. And all of these properties are affected by the interaction between the subatomic particles in the atom. So between the protons and the electrons with each other and things like that. And so the main driving force in what these properties are going to be is from Coulomb's law. And while many of you maybe haven't heard the name of this law, I think you're probably familiar with its basic tenet, which is that opposites attract. So protons are going to be attracted to electrons because they have opposite charges, and things that have like charges will repel. So 2 electrons that are close to each other in space are going to be repelling each other because they both have negative charges. Okay, so when we look at a given atom, we are looking at the interaction between the protons and the electrons, and between the electrons and other electrons within the atom. Okay, so there are 2 main factors that affect these periodic trends. The first is the number of energy levels. And you know that the periodic table gives us information about how many energy levels a particular atom has based on which row it is in, or which period it's in the periodic table. So the first row just has 1 energy level, the second row has 1 and 2, the third has 1, 2, and 3, and so on. And so the reason this matters is because Coulomb's law also tells us that as the distance between 2 charged particles increases, their attractive forces are decreased. So as we get electrons further and further and further from the nucleus, they're not going to be as close to those positive charges, and that's going to affect how attracted they are to the nucleus. Okay. The second factor is effective nuclear charge. Okay, so the nuclear charge is based on how many protons are in the nucleus. and if you remember, we abbreviated that as Z. Okay, and so we're going to call effective nuclear charge Z effective. And Z effective is slightly different than Z because it depends on, one, how many protons there are, but it also depends on how many electrons there are between the outer electron in the atom and the nucleus. Okay, because the ones in the middle are going to be repelling those outer electrons, and so they create a shielding effect. And shielding is the inner electrons, the core electrons, shield some of that positive charge that's in the nucleus, so the electrons on the outside don't feel the positive charge as strongly as they would if those electrons weren't in between. And you can probably see this a little bit better here with this illustration. So here we have the nucleus as this purplish sphere with a Z on it, and the electrons are shown as little blue spheres. And so an electron in the outermost shell is going to feel the force of attraction to the nucleus, which are represented by these blue arrows, but it's also going to feel repulsion, which is represented by the orange arrows, between itself and the electrons that are in between. So this is sort of like a game of tug of war, where the nucleus is pulling the outer electron in toward it, but in addition to having to use some force to pull it in, it's also got other forces pushing the electron back out at the same time. And so the way we represent this mathematically, just to give us a general idea of what Z effective is Z effective is equal to Z, which is just the number of protons, minus S. And S represents the number of shielding electrons. So this is going to be all of the core electrons that are in the atom. So now let's just do a couple of examples that can tell us or give us an idea how we would calculate Z effective. So if you go to your periodic table and look at carbon, for example, let's see what Z effective is for the outer electrons in carbon. And so carbon is number 6, and it has 6 protons, so we know that our Z is going to be 6. So now we have to figure out what S is, and for that we need to know how many core electrons there are in carbon, so that we know how many electrons there are creating this repulsion between the nucleus and the outer electrons. Okay, so carbon has electrons in the second energy level, but that energy level is not full yet. So we can only look at the ones in the first. So that means that we have 2 core electrons because it's just the ones in the 1s that we count. So Z effective for carbon is going to be 6 minus 2, which is equal to 4. So now if we go over a little bit in that row in the periodic table, take a look at oxygen as an example. Oxygen has 8 protons. It's an atomic number of 8. It also has 8 electrons. And just like carbon, it doesn't have a completely full second energy level. So we only have 2 core electrons, just the 1s electrons. So Z effective for oxygen is going to be 8 minus 2, which is 6. And so you can see as we move to the right across a row in the periodic table, our effective nuclear charge goes up. And that's going to affect our periodic trends, which we're going to talk about a little bit in class tomorrow, and get a feel for how these factors that we've talked about, both the number of energy levels and the effective nuclear charge, change the properties of atoms and create these trends that we see across the periodic table.